तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hi, this course on numerical methods and programming, we will cover some of the basic aspects of both programming and about algorithms. We will learn in this course how to convert some of your ideas into calculations on computer using some standard algorithms, and probably also learn how to design an algorithm towards the end of the course. Before we actually go into the algorithms, we need to know how to implement that on a computer, right? That's, we need to know some elements of programming. So the first part of the course would cover that. So the basic structure of the course is the following, that we would first look at this course has 3 parts. It's structured into 3 different parts, 3 main parts. Okay, each has its subdivisions. So the first part is just elements of C programming. We will only talk about C programming. There are many other languages which one can use, like Fortran, etc. But we would concentrate only on C, okay, C language. And the second part of the course is numerical arithmetic and error analysis. Okay, that's what the second part of the course would be. Okay. And the third part of the course would be some of the algorithms and its implementation. Okay. So we have basically 3 different parts. Okay, the first part would be C programming. So you would have learned by the end of the first part that at the end of the first part you would have learned how to implement an algorithm. Okay, so we'll first go through very basic features of C programming. We will not go through most of the complicated and deeper aspects of C programming, but some of the basic features of C programming. And then we would go through the concept of numbers on a computer and what is the errors which can come, how the error can propagate, and what is the care one has to take when one is actually writing a code, etc. And the third part would be just the implementation of an algorithm, okay, and some of the algorithms also. Okay. So let's start by looking at how do we create a C program. Okay. So there are basically 3 steps involved in converting your idea into what is to be done to a working program. Yep. Okay, so that is, first you have to create a source code, okay, in the form of some text file which is acceptable to a computer using one of the editors. Okay, you would type in this source code, okay, and then you have to invoke a compiler. Okay, in this case you would use a C compiler. There are many C compilers. We would use one of the C compilers, okay, to process the C code, okay, and make it into object file. Okay. So you could have many different parts of the code into different files. Okay, we will go through all those details soon. Okay, and those will be all compiled separately or together, okay, to form object files. Okay, and then you would link all these objects files together with other libraries and header files, etc., to form what is known as an executable. Okay, and it is this executable which we run on a computer. Okay. So that's the basic aspects, the basic 3 steps involved in running a code. Okay. So that's, I summarized that in the form of a flow chart, okay, here. Okay, that is, first we have a source code, okay, and then we would invoke a compiler, right, and then produce an object file, okay, that gives an object code, and then we would use a linker, okay, to link this object code, okay, with other object codes, okay, and also with other libraries, function libraries, okay, and then we would get a executable. Okay, so I guess that's clear. So this is what we would do in a to run a program. So the tradition is to use to create this object, this source codes, okay, with an extension .c when you are using a C program. It's not necessary, but that's a tradition. Okay. So we'll always write a file name as with a .c. For example, if you want to create my file, okay, myfile.c is an example of a C program file. And the compilation and linking steps, okay, can be, as I said, you first compile and produce an object code, okay, and then you link it, okay, or you could have both of them combined into one step. Okay, we will see that all in the later part of the course. So let's look at a C program, okay, and that uses a library and another function, okay, as an example. Okay, the best way to learn programming is through examples. So we would just look at an example of a C program. Okay, so here is a simple C code. Right. So it has different parts. Okay, you can see there is some include files here, some what's called the header files. Okay, and then you have a main part of the program here. Okay, and this program is basically computing square root of a variable x. Okay, and it's printing it out, and then it's calling a function. Okay, so it has some basic features of a complete C program. Okay, so it has a main part, and it does some computation here, okay, and then it calls another function. Okay, so that's what this program is. Okay. So what is this function? This function is in this form. So here is a function, okay, which I call print.c, and that function simply prints that this program is over. So that's what this function is going to print. Okay. So we will see how this can, we will just see this program and we will see how it can be compiled and how it can be run, etc. Okay, so this is sample.c. So here is this program. Okay, so it has that include files and it's stdio.h and math.h. Okay, and here I am not computing the square root of x, I am computing tan hyperbolic x. Okay, and it writes, instead of writing it into the screen, it writes it into a file called sample.dat. So this is a little more complicated than the simple code I showed. Okay, so it opens a file called sample.dat, okay, and then it prints it into that file, okay, and then closes the file. That's what this do. Okay, and it again calls this function. So now the question is, how do we compile this? Okay, so there are two ways of compiling this. They said here that you can first compile the programs separately to produce object files. Okay, so that's what we will do. Okay, so we say cc minus c sample.c. Okay, so that would create, so it would create a file called sample.o. Okay, and now we would say cc minus c print.c. Okay, so that would create a file called print.o. Okay, so we compile this print.c and we got a file called print.o. Okay, and then we would now put them together and produce an executable, and in the process we also link it to a library called -lm. Okay, so we link it to a math library by using this command. Okay, and we say -o, which means the output file, and that goes into this a.out. Okay, we can put any name here. Okay, like I could put my file itself here, then we will produce an executable called my file. Okay, so we will do that. So we can say cc sample.o, sorry, print.o, okay, -lm -o a.out is what I use. Okay, that would create this file called a.out. Okay, Okay, the a.out is a file which has been created by this compilation. Okay. So you could also do this in one step. Okay, so that's, I'll show you. I'll remove this a.out. Okay, and I could say cc sample.c print.c minus lm minus o a.out. Oops. I made a mistake. A.out is one a.out. Okay, and then you can see that it has created a.out again. Okay, so now to run the program, I would just say /a.out. Okay, so it printed on the screen. The print program is over. That's because I had given in the print.c. Okay, so remember the print.c is just printing this program is over. Okay, so what did this program do? It actually computed tan hyperbolic x for all these values of x. Okay, and it wrote it into a file called sample.dat. Okay, and then it called this program function, this function print init. Okay, print it. Okay, and the print it is basically just printing out that this program is over. That's all it is. Yeah. Okay, so that's what we did, and we saw the two ways you can compile it. You can actually compile it by invoking -c command, which will only do the compilation. Okay, and if you don't use this -c, and then it would compile and link. Okay, so and both will be done together here. Okay. So for example, here we are not linking it. That's why we don't have to use -lm command. Okay, so here we are linking, so we have used -lm command because it is linking to a math library. So let's see what happens if you don't link it. Okay, so let's say I don't like linking this program with another library, so I just do this. Okay, so then it says that it cannot understand tan hyperbolic. Okay, so the tan hyperbolic function is built into a library, math library. So we need that math library to compile this program. So for many other mathematical functions, you need this math library. For some other functions, you might need some other library. Okay, so we would use those libraries all with the -l command. Okay. So these libraries are all stored in a different part of the computer. Okay, so it will be stored in a region called, for example, in a Linux platform, it will be stored in /user/lib. Okay, so it could be in a different program, in a different operating system. It will be in a different place. Okay. So all these libraries are stored there, and we are just linking them to that library, linking the program to the library. Okay, so we need to use -lm command if we are using math functions. Okay. So similarly, we saw in this program that we are using these header files. Okay, so what's the use of these header files? Okay, we can see that by just removing this header file. Let's say we remove the stdio.h. Okay, and then try to compile now with the -lm, of course. Okay, so then it says it cannot understand these things, file, fp, etc. Okay. So all that definitions, okay, that is, we say this file statement and this open statement, all the statements are actually put into the stdio.h file. Okay, so that's required if you want to use this these statements. Okay, so of course for the simple printf statement you don't need it. In some of the compilers, all these statements are actually built into the compiler, and you don't need a separate header file. Okay, so it's a good practice to always put this in here, because some compilers need it, some compilers don't need it. Okay, so if you want your program to be kind of compiler independent as much as possible, then you put this into the program. Okay, so that's a basic idea of how do you create a program, and how do you compile it, and how do you run it. Okay, so we saw that we have this very simple code. Okay, and there are two functions, and with another function. Okay, we compile that and we would run it. Okay, so that's what is done. Okay, so as I said that in this linking command, to summarize what I said, in this linking command we used a library. Okay, it's an archive, math archive called m.a. That's what we did. Okay, so we also saw what is the need of this header files, and what is the need of this -lm command. Okay, in this thing. Okay, so now let's look at the anatomy of the program. So let's summarize this. Okay, so we had some compiler preprocessor commands, and that's what I said, all this include files here. Okay, and then you had a main function, right? right, with some name to a function. You can give a main function, okay, and then you had some variable declarations, right, and then you have the code, the main code, okay, and then you could have sub functions. In the previous example, I had put the sub function separately, okay. You could also include it into the main code, okay. So in the one file, into the main file, okay, that is in one file you could have the main program or the main function I call, okay, and sub functions, okay, or you could have them separately, okay, and again it's a good idea to have this sub functions separately, okay, and you compile them separately and then you link them together, okay. That's always a better idea. I'll tell you why later, okay. It's always safer to do that, okay, that to have the sub functions separately and then do that. For such small programs as the one which I'm going to show here, it may not be important, but for big programs it's always good to have sub functions separately and compile separately, okay. And in the sub function has the same structure, okay. It might have some arguments which you pass into it, okay, and then you have the argument declarations here, okay, and then you have the variable declarations which are private to the sub function, and then you have the main code there of the sub function. We will see examples of this, okay. So how we do this, okay. So before that, let's go through each one of these things in a little more detail, okay. For example, let's see what is the compiler preprocessor does, okay. So as I said, the compiler preprocessor basically handles the first part of the program, okay. So that is the stdio.h, math.h, all these header files, okay, are actually handled by the compiler preprocessor, okay, everything with an include command, okay. And then the second filter of the compiler, that is as I said here, the compiler has about 3 or 4 filters, okay. The first filter is the preprocessor which handle that, and the second filter actually checks the code, okay, and it checks all the code symbols, statements, all things are checked by the second filter, okay. And the third generates the code, which generates a machine a code which is understandable to the machine, yeah. And there can be a fourth filter which actually does the optimization. It improves the code. It actually modifies the code, okay, and it improves the code, okay, and such that it will run faster. Okay, so there can be these 4 filters, okay. The fourth one need not be there. It depends on whether you invoke it or not, okay. So that's the 4 parts into the code, okay. So let's look at so that's a basically compiler preprocessor which we looked at. Now let's look at the variable declarations, okay. So now what is going to be the variable declaration? We have seen in this code, okay, we have said that float xy. Okay, so is that the only variable declaration, the only type of variable declaration which you can make? No, there are many types of variable declarations. Okay, so that is, in general, it has this form. That is, it has a class, okay, and it is a type, okay, and then it needs a name. Okay, so that's and it could also have an initial value given to it. Okay, so the C language, unlike other languages, okay, require all variables to be declared, okay, before you start the program, okay. All variables has to be declared, which is good or bad depending upon what your use is, okay. So everything has to be declared, okay. So and the declaration is of this form, that is class, type, and a name and initial value, okay. The initial value is not compulsory. For example, here I given an example, say auto, that's a class, okay, float is a type, okay, and then you have a trial as a name, okay. So you could declare that as auto float trial equal to 0.0, okay, or simply auto float trial, okay. Both are possible, okay. Now what happens is auto, okay, so we will see that in the next slide, okay. So there's more details about the class, okay. So auto variable is actually a default. If you say float, it's taken it as automatic, okay. So that's a default variable declaration. Okay, so let's look at some of these examples here. Okay, so here I have declared it's a similar program as the one before. Okay, so here is the header files, etc., and there's a main function, and then we also have a sub function here. okay, and I have declared this variable float xy, okay, no initial value is given. Okay. So this actually means auto float x, okay, and you have to declare more than one variable in one line, you just separate them by a comma. Okay. So you can have any number of variables put in here. Okay. So I have done 2 here, okay. And in the C program all lines are separated by a semicolon. Okay. So here is a declaration of the auto variable. Okay. So now this variable declared as an auto variable is private to this function. Okay. So unless you make an effort to pass it to something else, it will not go out of this function. You could have the same variable declared in another function. Here is a sub function I have declared. Okay. For example, float y. The y value it takes inside this is different from the y value it takes from this. Okay. Unless you have passed it back. Okay. And in this function we are actually doing that. Okay. So here is an example of the use of an auto variable. Okay. So in which you declare the function here, the x value takes starting from 0 in steps of 1, okay, it increases the value. It's a floating point variable. Okay. Now what is a floating point and what is an integer, etc. we will see in the later class. Okay. When we talk about arithmetic, how is a floating point actually stored in the computer, how is an integer actually stored in the computer, we will see that later. Okay. So right now it's a floating point is a real number, okay, and it's an integer. Okay. That's what we have 2 different types we are going to use. Okay. And we will go to that later, a little later again. Okay. So here is a floating point, okay, and that takes value 0, 1.0, 2.0, etc. here, and this function actually computes the cube of that. So it just finds the cube of that function, that value variable, and returns it to this function, and this it just prints it. Okay. So it actually prints. It also uses a built-in math function called power. Okay. So it finds the power, the second power of the variable x, okay, and I have here made a program to compute the cube. Okay. So if you actually execute this program, you will get the square and the cube both. Okay. So we will see that here. So we say cc sample1.c minus lm again we need to do, and minus o a dot out, okay, or I could call it something else, a dot out I call. So if I do that, okay, it prints out the number x value and its square and its cube. Okay. So now here suppose see now here when I pass this variable, right, this function actually calls it. Okay. When I call this function, I pass that variable x. Okay. So I said that in the beginning, that when you have a sub function, okay, and you have to declare the variable declaration of the variable which has been passed onto that function, that has to be done here. Suppose we don't do that. Okay. Let's say we don't have this here. Okay. Then what happens? Okay. So if you don't do that, do we get the same answer? So we compile that again and we run that. Okay, we get 0. Okay. So basically it doesn't know what the value of x is, right? So because we are not passed it, so it has to be passed. Okay. So when you have a sub function, okay, the sub function should declare this auto variable has to be declared inside that sub function separately. Okay. So that is the auto variable use. Okay. So then you can have external variables. Okay. So external variables are common to the whole program. Okay. So you have many sub functions and functions, okay, and you want a variable to be shared by all this program, okay, all these functions. Okay. Then you could declare that as external. Okay. Then it will be shared. Okay. But then you have to tell the sub function that this variable is declared external, otherwise it will not know. Okay. So that we will see that. Okay. We will see that with another example. Okay. That's the best way to look at this. Okay, so here is a function which uses the external variable, okay, and this is the main program. Okay, now I have declared float z. Okay, so that's again a floating point. The z is being declared as a floating point, and I have declared it outside the main function. Okay, that's where you declare the external variables. Okay, you declare them outside. Okay, you don't have to say external there. You just declare the variable which you want to use outside that outside the main program. Okay, so now this program actually calls. Okay, so I have declared that inside here as external float set, because this main function is going to use this thing. So I have declared that variable as external in the main function. Yeah, and now there is another sub function here which this program calls, and that's called add x. Okay, some other function called add. Okay, so that function, which I would show you here, okay, has also using this variable x. Okay, so variable z. Okay, so I would say that external float set inside that function. I have to say this. If I don't say this, this function will not know what z is. Okay, right? Okay, so and it's an external value. It will share that value with it. Okay, it will share the value with the. So if the z value is changed here in this function, okay, it will also get changed in the sub function here. Okay, so that's what we are going to. So now if you want to compile this function, so we'll use cc sample3.c. I'm not using the object, not creating the object file. I just do everything together. So okay, so it creates it runs this program. So let's see what happens if I remove this here. Okay, so if I don't have the declaration here, and then and of course it doesn't understand what that is. Okay, so now we could change the value of the function here. Okay, so we could have it. So what we could do is we could just give it a value here. Let's say z equal to 6.0. Okay, and then we'll save it, and we declare that in here. Okay, and then we will see that this what value it gets now would be different. Okay, so because we have changed it in the main program itself. Okay, and it has been shared with this sub program here. Okay, the C program is case sensitive, so you have to be careful with that. Yeah. Okay, so that is. So I'm printing out something different. I should print out inside this program. I should print out. I will make a printf statement here. Just to see that when we change it in the main program, it also gets changed here. Okay, so it prints out 6 here. Okay, because in the main program you change it, it changes here also. Okay, so that's what we wanted to see. So that's the external variable, and then you can have what's called. Okay, now this is again the summary of how do we use the external variable. So we declare it outside the main function, and any function which uses it, you will declare it external. Yeah, so that's a external variable, and then you could have static variables. Yeah, okay. Now static variables are also very special definitions. Okay, now if you declare a variable as static, okay, inside a subprogram, okay, now that variable is changed exactly once. okay, that is the first time it enters that subprogram, okay, that variable is changed. After that it remains static. Okay, so we will see that again with another example. So here is a function which uses which uses the variable static variable here. Okay, so I declared the function of the variable here as y equal to 0 as static. Okay, so that means it would initialize this variable, okay, the first time it enters this code, okay, and after that it will not. Okay, so what happens if you run this? Okay, so that is, so we'll run this cc sample2.c. Okay, so it prints 2, 4 and 6. Okay, that's what it's doing. Okay, so first time it enters it got 0 and then it's just adding 2 to it and then printing 2, 4 and 6. Okay, so let's see what happens if you don't declare it as static. Okay, so then since it is initialized every time, just keep printing 2, right? That's what it will do. Oh, that's what we expect it to do. Okay, so that's what it does. Okay. So that's a static variable. It's very useful to have this definition. Okay, there are many cases. For example, in the case of random number generators, etc. Okay, you have some kind of a seed. Okay, and use that seed to generate a random number. And the next time whether you call it random number, it doesn't want to again initialize the whole process. It wants to generate a new random number, not the same random number. So it wants to initialize it only once. Okay, well, the first time you call that thing. Okay, so that is for that kind of functions. It's extremely useful to have something defined as static. Okay, so we need this definition of static. So we just now saw that we have auto variables, right, and we have external variables and we have static variables, and I think that's the basic 3 classes which you would need to look at. Okay. So going back to our definition, so we had the class, okay, and then we have type and we have name. Name we already saw, okay, x, y, anything is a name, okay, so we can put in many names. It's only that we have to be careful that it is case sensitive. Okay. In the C program, the variable names are case sensitive. Okay. So whether you use uppercase or lowercase letter, they're different variables. And initial value, we saw that we can put the initial value, we need not put the initial value. Okay, so that also is up to the programmer. Okay, now the second thing is the type. Okay, so we also saw, I already showed you some type here, for example float. Okay, that's one type. Okay, so what are the main types of variables which you can declare? Okay. So here is the summary or the chart of various data types. Okay, so you could have an integer, okay, or you could have a floating point, right? So that's what we saw, a real number or an integer. Okay. Or you could have characters. Okay, so characters are declared as char, okay, integers are declared as int, and floating point as float. Okay. Now there are two different types of integers which we can declare. We can have long integers and short integers. Okay. So now we saw that in most of the recent compilers or the present day compilers, when you declare an integer int, it's always a long integer. Okay. So that means if you have a 32-bit computing, okay, then you have 2 to the power of 32 is the largest integer which we can represent. Okay, unsigned integer. Okay, if it 1 bit is actually used for the sign, so we can actually have 2 to the power of 30 or 2 to the power of 31 as the biggest size. Okay. So we have the third type, that is actually the unsigned Okay, so we don't use that one bit, which is, we can also use that bit which is reserved for the sign to represent a number. That's why unsigned. Okay, so unsigned can be a little longer than the long integer. Okay, and then you have the floating point. Okay, the floating point also there are two types. Okay, you could have the single precision or double precision. Okay, so when you say float, that's single precision. Okay, and then you say double, that's double precision. Okay, we'll see the difference in a program. Okay, that's the best way to see it again. Okay, or then you could have characters. Okay, so that's what I say. You got 32-bit or a double precision in the floating point. Okay, and then you have characters. Okay, so that's the basic data types which we would have. Okay, so let's use a let's look at a program which uses all these data types. So here it is. Okay, so you have double. Okay, x and y. Okay, have been declared as double. That's floating point double. Okay, auto variables, and then I've declared them as long integers. As I said, in these, especially in the compiler which I have on this machine, whether you use integer or long integer, it gives the same thing. Okay, but it will not be true in all machines. So maybe if you are using large numbers, it's advisable to use it as long. Okay, long integer is also represented just long. Okay, you don't need to write long in int. So these have been declared as integers. Okay, and then I have a character, which is the letter. Okay, it's called a character. Okay, so this has been declared as a character. Okay, this is a name. Okay, I have another character which is a character array. Okay, or a character string. Okay, for example, a quick fox. Okay, so that is a string which I call chain. Okay, so these are examples of character declarations. Okay, so you can declare a single letter character. You can give any name. I just use letter here. Okay, or you could as a chain or an array, okay, or a string of characters. Okay, so this program uses, now I define letter as b. So usually in single quotes, character is assigned. Okay, so this letter which is declared as a character has been assigned a character b. Okay, and this letter, this integer I has been assigned a number 2. Okay, and then I'm just printing them out. Okay, so then this example also demonstrates how do you use print statements. Okay, so printf is actually print on the screen. Okay, or as I shown you in the previous example, you could open a file and use an fprintf, that is printing into a file. Okay, so this example also demonstrates that you can print it onto a screen. Okay, and now here is a format of the print. Okay, here is a format for the print. Okay, so if you are printing a double precision number, okay, you use lf. Okay, or you could use e. We will see what the differences are. Okay, and for a long integer you use ld. Okay, percentage ld. Okay, that's what you need. Okay, and the C program, if you give wrong type here for the print, okay, it will print basically junk. Okay, it will not screen, but it will print junk. Okay, in a C program, the characters are printed using a %c. Okay, and the strings are printed using a %s. Okay, that's a format. Okay, so now we'll run this, and then we'll see what it prints. Okay, so here, and the program has program continues. It has a loop. Okay, and in which the j values increase from 0 to 31. Okay, and it does, and the j value is initialized to 0, and it goes by steps of 1 up to 31. Okay, and the x value, the y value is which is equal to 1.01 to start with. It computes the square of that. Okay, and assigns that value to y. Okay, so basically just keep computing the square, that is 1.01 square and the square of 1.01 square, etc. Okay, so we will see how long it can go before it blows up beyond the capability of the computer. Okay. So what I want to show you is that this floating point and this integers, okay, there is a limit to the size or to the size of these numbers which the computer can handle. Okay, because it has a finite precision. Okay. So that's what we are going to see. So let's look at that in this example. Let's compile this and then run it. Okay, so we'll compile this again, this time sample 4. Okay. So here I have not given any minus O. By default it creates a dot out. Okay. If you want some other name, then you have to give a minus O, otherwise it will always create a dot out. Okay. So dot slash a dot out. Okay, so now this prints, you can see that it prints as the loop goes. Okay, first it prints the number y, okay, and the integer I, okay, and the letter which I assigned as B, okay, and the string a quick fox. Okay, so it printed all that. Okay, then it enters into this loop. Okay, remember that's the first statement was to print all that things. Okay, that is the y, I, and the letter and the chain. Okay, so that's printed. Okay. And then it goes into this loop and it prints it every time. Every time it squares, it prints that. Okay, so that's the next part. Okay, the next part you can see. So that's what it's printing. Okay, it prints 1.02 and 2, and then it squares that. It keeps squaring it. Okay, and here it takes the power, 2 to the power of n is what is being printed here. Okay, and you can see that it can go. This is been declared double precision. So you can see that it goes all the way up to 16, and then it can't handle it anymore. Okay, by the 17th loop, okay, it has gone to infinity. Okay, as far as computer is concerned, okay, it's infinity. Okay, infinity has been reached. Okay, and the integer continues, the square. Okay, so that's the power 2 to the power of n, and it can go all the way up to 30. Okay, 2 to the power of 30 is the largest integer which it could print. Okay, it cannot do beyond that. Okay, then it gives junk. Okay, so this is a warning to C program users. Okay, that you have to be careful when you're using large numbers. Okay, so you get 2 to the power of 31. It is not screaming. It is not saying it's infinity. It's not telling you that it's not a number. Nothing. It's just giving you a minus 214748368, which makes no sense to you. Okay, so that's the thing. Okay, now let's change this and then let's make this just a float, that is single precision, that is float. Okay, and now let's see what it gives. We'll compile it again and we run it. Okay, so now you see it couldn't go beyond 13. Okay, it went up to 16 last time. Okay, so beyond 13 it cannot go, it's already infinity. Okay, so if you want to use larger numbers, okay, and you want to also keep more precision, that is the number of decimals you want to keep after, number of digits you want to keep after decimal, then you have to use floating, you have to use double. Okay, so that's the two different data types of the floating point and this integer types which I want to show. Okay. Unfortunately, I cannot demonstrate the difference between short, long, and unsigned on this computer, at least on this compiler. Okay, it's by default it uses long integer, and what you use any of this, okay, you will get 2 to the power of 30 as the largest integer which it can handle. Okay. But that will not be true in other machines and other compilers. Okay. So going back to the basic program. Okay, so that's a summary of the program which we have so far seen, right? So we had again to say that we had include files, and we saw the use of a main function and a sub function, and then we saw how you declare variables, okay, and how do you use print statements, etc. So as I said, this is a header file which have been handled by the preprocessor, okay, and here is the variable declarations, okay, and now I want to tell you something more here. Okay, now this is a constant assignment. Okay, so you are assigning here a constant z equal to 2.0 by 3.0. Okay, so now z is a floating point. Okay, so now for us, if you write z is equal to 2 by 3 or 2.0 by 3.0, it's the same. Okay, z is a floating point, it's a real number. we know it's some point something, right, 0.6 something, okay, we know that. But for the computer, okay, they're different. Okay, so if you write 2 by 3, okay, and then even if you take ratio of two integers, okay, and then the computer assumes the result is an integer or the nearest integer. Okay, so if I declare z as 2 by 3 without 0.0 by 3.0, then you are going to get 0. Okay, if you just say z is a floating point and it's 2 by 3, then it is 0 for the computer. Okay, so it has to be, you have to be careful, you have to say 2.0 by 3.0. Okay, and so that's a constant assignment. Okay, and you can also have, for example, here you have all this also is an assignment statement. These are called assignment statements. You are assigning something y, some value to y. Okay, these are called assignment statements. Okay, so that's the basic summary of the code. We'll conclude today's lecture by looking at this anatomy of a program once again. That is, here is the summary of a program. That is, first we start with compiler preprocessor commands, okay, which you might remember means that a standard C compiler has its 4 filters, and the commands which takes care of the first part is a preprocessor commands, okay, which includes which is actually the inclusion files, etc. Okay, so we'll look at that program again, and then we will see that once again, okay, what these things mean. Okay. And then we have the main function, okay, with the function name given there, okay. And the main function will have variable declarations and the main code. Okay. And then you could have many such sub functions, or may not have any functions at all, sub functions at all. Okay, so let's look at what meant by variable declaration. Okay, so in variable declarations we would have we would declare the variable with a class and a type and a name, and sometimes with an initial value also given. This is not necessary, but sometimes this also can be given. Okay. So we look at all of this through a sample summary program, okay, and that is shown here in this, which I made this program, which summarize what all things which we have looked at now. So first here is the preprocessor commands, which says that here include the standard IO library and the math library. Okay. And then I have one declaration here of a variable. So we will look at this what these declarations are one by one. Okay. So here is the main program. Okay. So that's sometimes we do, as we saw earlier, that we have external variables. We declare the variables outside the function. Okay, and that's shown here outside the main function. Okay. And if it is not external, then they are declared after the main program starts. Okay, so here is the declaration of a floating point variable, variables x and y, okay, with type float and class auto, right? And then you have an integer variable declared. Okay, and now I am using this external variable. So as you may remember that we have to declare them again here. So that is external type variable, which is external class, and then float is a type, and then z is the variable. So float is declared outside the main function because it's an external variable. So and then we have functions, sub functions here. There are 3 sub functions here. Okay, they are called cube, add, and increment. And note that these sub functions also have a type. It's a floating point variables, floating type. Okay, and the reason for that is that these sub functions actually return something to the main program, as you can see here. For example, the cube, this sub function, okay, and this cube actually returns this variable y, which is of the type float. Okay, so the function itself has to be declared of that type. And so that's the floating point, that's the sub function calls. Okay, and then here is another declaration. So this is declaration of the sub functions, and your declaration of the variables, the auto class and the external class. Okay. And then here you have a declaration of a file pointer, okay, fp. Okay. And then this file, after the declaration, you have the first assignment statement, which is fp is now the file pointer is now used to open a file called sample.dat. And here is a static assignment, sorry, an assignment which gives x as value 0.0. So now, as I said earlier, remember that you could also use this this initialization, you could also do it here. You could say float x equal to 0.0 to initialize this function. And then there is this program has a small loop here, okay, in which you compute tan hyperbolic of the variable x. Okay. So that is the assignment statement here. Y, which is declared as a floating point, okay, is now assigned to tan hyperbolic of x. Okay. X is another floating point. So tan hyperbolic is now here a function. Okay. Now this function is not declared anywhere here because it's part of the standard math library, and that's what we have used here using this math.h. Okay. This is part of the standard math library. Okay. So now this demonstrates the use of a function from the math library, and here is a way of using. Now once we calculated this, here is the method to actually write it onto a file. So I use fprintf to write it into a file fp. Okay. And in that fp I write apart from some comment which says module 1, that is this part of the, it is to know that it is this part of the program which is writing this. Okay. And then there are two floating points which is now commented by %f and %f, right. So that is to say that there is a floating point which you are writing, and that is x and y. And then we close that file fp. Okay. And now here is another function which I call, this is another function which doesn't return anything. Okay. So it's actually void. So if I actually declare it here, I should declare it as void, but many of these compilers you don't have to declare it, but many of the older compilers you will have to here say void. For example, here you will have to say void, sorry, you will have to say here void print init. Okay, that's the correct way of doing it, but many of these compilers now assume when you don't declare it that it is indeed a void function. So now here is another loop. Now this is a way of calling a function which is now this this loop again does similar to the earlier one, this loop, but here now we are calling this function cube of x, right? And now that is something which I have written, and that returns the value a floating point, and that floating point is assigned to this, and this program simply now prints it out on the screen. Okay. Now here note that I am using printf instead of fprintf. So if I run this program, it will simply print this on the screen. Okay. So we can see that here if I run this program. So I have this program compile and it runs this. Okay. When this program runs, it just prints it on the screen. It's module 2, it's printing the variable 5. Okay. That's the x value and the square of that and the cube of that. Okay. And that is what this program is, this part of the module 2 is actually printing, right. So it's printing that x variable which is 5 because it went up to 5 up to 4 here. Okay. And it starts from here at 5. Okay. And then so it prints out 5 and the power 2. Then now this is again a function which is part of the math library. So it is power x square, it computes x square power x2. So this x square is part of the math library. So it is again to show you that you don't need to declare something like this here, okay, and then put it into the print statement. You can also put the assignment statements straight into the print statement if you want to, if all you need to do is just simply print it. Okay. And then here y is the cube of x. So I could have simply put cube of x here to print it out also. Okay. And then here is another program which is called add of x, okay, which is something which is part of this thing, a sub function which it calls, okay, with starting from x equal to 0, and so I initialized x equal to 0 again here, and okay, and I pass it into this y of y, so to add of x, and it returns something, and that's printed as y, and I print that out x and y here. So you remember I'm putting it here as x equal to 0, and then I pass it here, okay, and it returns something. So what does it return? Okay, so if you look at this, you will see that add of x actually what it does is it takes the value x, okay, and it adds that x and y together. So y is now initialized here to 0, okay, and then it increments y by 2, okay, and then adds that to x. So remember x is 0 which is passed, so it's x plus y is what it's supposed to return. So the next time, so now y here is a static variable, so the next time when it is called, it is not initialized. So this program is just to demonstrate the static variable. Okay, so that it's this variable y is only initialized once. Okay, so you can see that again when we run this code here. Okay, so that's part of the module 3. So you see you're passing x all the time as 0. Okay, x is always passed as 0, but what it returns is 2 4 6. Okay, 2 4 6 module 3 you look at. So if you look at module 3, you will find that its x is passed always as 0 here. Okay, but what it returns is 2 and then 4 and then 6. Okay, so the reason for that is only in the first call the y here is initialized. Okay, the next time, even though we have written y equal to 0, that is initialized only the first time it is called to this function. Okay, and the next time it's called, it's incremented by 2, and then so z goes from x plus y, but x is always 0 because it's passed as 0 here. Okay, so z goes as 0 2 4 6 etc. Okay, so that is what is this demonstrating. So that shows us how to use floating point variable, auto variables, and also external variables. Okay, like this external variable, and also how to use static variables. Okay, and we will continue on this programming in the next class.